Good morning, everyone. Today we are going to discuss epitaxial growth. This is lecture 27 of year 32. So epitaxy is meaning the growth of single crystal film on top of a single crystal subject. Epitaxial itself means upon orderly arranged. So this is word from Greek. So the underlying crystal structure or subject structure continued into the thin film layer on top of it. So we use many different ways to grow epitaxial layer. So many we use CVD, chemical vapor deposition. One of the chemical vapor deposition variations. So the chemical vapor deposition, like thermal CVD we discussed, and its variations like PE CVD, rapid thermal CVD, metal organic CVD, the ARD atomic layer deposition, ultra high vacuum CVD, laser optical X-ray acetate CVD. There are also non-CVD methods like MB, IB, this molecular beam epitaxial, IB ion beam epitaxy, and clustered IB. Basically, all compound semiconductor technologies require the use of epitaxial layer for device processing. And also for some silicon approaches, we also use epitaxial layer. So in practice, many devices fabricate entirely within epi layer, like a bipolar junction transistor. And in most devices are fabricated on silicon substrate directly. But for VLSI fabrication, it is good to use epi layer for better control. So for example, here we show a structure of bipolar junction transistor with epi layer. So we have a subject. And then we grow a thin layer for n-type material on top of it. And this n-type epitaxial layer will work as a collector. And then we do the doping and make the P rhodin and iron rhodin. So it is work as a barrier layer for this bipolar junction transistor. It reduces the collector resistance and keep their high breakdown voltage. And this is only available with epitaxial layer. For CMOS fabrication, this epitaxial layer on top of a body or the subject has many advantages over compared to the polished bark wafer, a PBW we call it. So for this CMOS epitaxial wafer, it can improve the latch-up immunity. So basically, the latch-up meaning the resistance between the source and between the power and the ground, or source and the ground, power source and the ground. So if we increase, decrease the resistance, actually, so basically they are connected. They will be leaking, and the device will stop working after some time. And by using this epitaxial layer, because the epitaxial layer has high impurity, low defect, so it actually will just improve this latch-up impunity. The epitaxial layer also is free of silicon oxide precipitate, free of crystal or originated particles, COPs, or we can say condensates. So those precipitate COPs, so they are formed during the crystal growth. And so if we use the bark wafer, the poly bark wafer, these are the problems. But you use the epitaxial layer, it's eliminated. They are eliminated. Also, the silicon surface of epitaxial layer is smoother than polished wafer, polished bark wafer. There's little surface damage. And in this structure, this CMOS device fabricated on an substrate. On top of it, there's epitaxial layer. And then the device is fabricated in this epitaxial layer. So there are two types of epitaxy, homo epitaxy and hetero epitaxy. So homo epitaxy is shown here. The film and the subject have the same material structure. And this is often used in silicon on silicon growth. So there, as I mentioned earlier, so epitaxial layer is purer than the subject. And also it can be doped independently. If the structure of materials are different than the subject, then we call it hetero epitaxy. So like here. So these two are epitaxial layers. So the first here, this is the strained hetero epitaxy. So meaning the structure, so we have this, because the structure are different, or crystal structure are different. So the newly grown structure is strained. And on the right, this is the relaxed structure. So meaning there is less strain. A good example is aluminum oxide on top of gallium arsenide girth. So this is especially useful, especially important for 3-5 device for compound semiconductor devices fabrication. So this is the main reason because we want to ban engineering. And for optoelectronic devices. And here we show the basic vapor phase epitaxy system. So vapor phase epitaxy system, you can see actually it is very similar to a low pressure CVD. Low pressure CVD is a thermal CVD. So this here is a thermal CVD. So in this system, so we have this chamber, and we have our the wafer. So rests on this susceptor, and this susceptor is heated using IF coil. And then we have gas supply, so hydrogen, and dichlorosilane, and then we have boron. This is the dopant, provide the dopant, and it's controlled by a mass flow controller and some valves. And we can provide vacuum pump, so to make it low pressure. But some system there's no vacuum pump. So this is a basic vapor phase deposition, vapor phase epitaxy system. So simply it is a thermal CVD. Sometimes it's low pressure thermal CVD. So this VPE is most commonly used in silicon epitaxy in IC fabrication. So we use thermal energy to drive the chemical process, typically around 1000 degrees C. So because in this at this high temperature, so the impurity can diffuse into the subject, into the F layer. So we must minimize the impurity concentration in the growth chamber. And typically, it's done in high vacuum, and also we can use load locks, so or small moving box to transport the wafer into the larger chamber. It is very attractive for the growth of thick layers. The biggest problem for VPE is the lack of in situ real-time growth diagnostics. So in order to make it clean, so there's several steps we need to be done before the VPE process. So mainly we need to clean organics on top of the wafer, the silicon wafer, make the silicon subject surface very clean. So this can be done by using oxidation method. And then we remove the silicon dioxide. Okay. So for the chemical reactions of VPE, so we can simplify the process. We use the thermodynamics to analyze VPE process. So the analysis is very similar to silicon oxidation process. And we use the Deer group model for oxidation, for thermal oxidation process analysis. And for VPE, we can also use the Deer model. So basically, here the silicon, and here we introduce the gases, and the flux of the deposition species across this boundary layer or stagnant layer is equal to the flux of reactant consumed by the growing surface. And then we can write F1, this is flux 1 equal to flux 2. And then we can, F1 equal to Hg, Cg minus Cs. This is exactly the same as thermal oxidation analysis. So Hg, this is the mass transport coefficient. Cg, this is the gas concentration of reactant. And Cs, this is surface concentration of reactant. And this is equal to F2. So F2 is the consumption of the reactant. And Ks, Cs. Ks is surface reaction rate. And Cs, this is gas concentration of reactant. So by equal, F1 equal to F2, and then we can get F equal to this part. So we can simplify when we can get this F. Total F1 equal to F2, and then so equal to this one. And then the growth rate equal to flux over N. And N is the number density. So we came to this number density many times. So you define as the density of silicon, mass density divided by number of silicon atoms divided by growth molecule. What's this? Number of silicon atoms. So number of silicon atoms divided by the growth molecule. That means the number in the number in the in the molecule. So like SiO2. So like oxygen has number 2. Okay. So we have the silicon density over a number of silicon atoms over growth molecules. Okay. And this is a number density N. And we Actually, we mentioned this analysis when we talk about APCVD. And when Ks is much greater than Hg, and then it's transport limited regime. And when Hg is much greater than HKS, it's reaction limited regime. So basically, we have two factors to limit this process. And the slowest one, there are two rates, right? So the slowest one control the total rate, the total deposition rate. So, and the Beer group model actually is very simplified model, and only consider the thermodynamics. Actually, in the VPE process, so there are a lot of chemical reaction happening. So we need to consider this detailed chemical reaction to get a better analysis of the full process. So similar to APCVD or thermocivil, it's basically a thermocivil process. So we have like the precursor, gas, decomposition, introduce the gas into the chamber and decompose the gases, and then transport the surface to the surface of the wafer, the second step. And at the surface of the goods, the species must absorb, diffuse, decompose, and reaction. Finally, the byproduct is dissolved and transported outside of the chamber. The full process is very similar to what we discussed, APCVD. So for silicon growth, very important for CMOS IC fabrication. So the silicon source gases, mainly we use chlorosilane. So chlorosilane expresses silicon, hydrogen, and chlorine. And then we have X number, and then 4 minus X. So X equal to 0, 1, 2, 3. So there are variations of this chlorosilane. For example, we have, or there are basically 4 types. So with the X equal to 0, 1, 2, 3. So like silicon tetrachloride. So SiCl4. And then we have H equal to 1. This is a trichlorosilane, so TCS. And then we have H equal to 2, equal to the X equal to 2. This is a dichlorosilane, DCS. And then we have for H, the X for H equal to 3. So this is silane, this silane. Yeah. So if we increase the X number, and then we can decrease the required reaction temperature. So for example, for silicon tetrachloride, the temperature, the required reaction temperature is high. It's 1150 degrees C. So now the DCS is mostly commonly used source gases. So for the reaction part, primarily the components include hydrogen molecule, hydrochloric acid, and silicon this dichloride. So this is the SiCl2. This is the main reactive species. So the whole full process, basically we have silicon dichloride in gaseous form reacts with hydrogen in gaseous form, and it creates silicon in solid form, and also HCl, hydrochloric acid. So the reaction is in dual directions. So the dual directions, like for silicon dichloride react hydrogen and generate silicon, and this is the deposition process. And on the other hand, if silicon can also react with the hydrochloric acid and use their generate gases, hydrogen and silicon dichloride. So this is the etching process. So basically, there are two processes: so deposition of silicon and then decomposition of silicon, or etching process. So we can control their reaction rate, for example, by adding Epitaxial hydrochloric acid to slow the deposition and increase the etching. In reaction limited regime, so the reaction rate R equal to C1, the partial pressure, silicon dichloride minus C2, partial pressure of Epitaxial squared. So here we use minus. This is because the etching is opposite process of deposition. So we use minus. And if we increase Epitaxial, and then increase etching and decrease deposition. Now this figure shows the silicon deposition rate as function of mole fraction of silicon tetrachloride in hydrogen molecules. And this figure shows the epitaxial silicon growth rate change. So you see this similar figure before. So we have a mass transport regime and a surface reaction regime. So and there are three curves. There are three curves, and we have so here we have the number x for each the hydrogen different. Like here, this h equal to 1, and here h equal to 2, and here equal to h, here h equal to 4. So h increase the number of h, and the reaction or growth rate will be increased. On the other side, if we increase the number of chlorine, and so the etching will increase, and then so it will be etching the reaction rate and the growth rate will be decreased. So for epitaxial layer, we need to introduce a dopant, like make it N-type or P-type, right? So we want to make their collector, we want to make their make it either N-type or P-type. So we need to introduce the dopant source gases. So here we have a list of dopant source gases. Like you want to introduce boron, we use diboron, so B2H6, and make it a P-type material. And then if we want to make it N-type silicon, so we can introduce phosphine so we use phosphine to introduce phosphorus. And also we can use arsen to introduce arsenic. And typically all these source gases are diluted using hydrogen. And I just want to quickly introduce this epitaxial process, especially the VPE, vapor phase epitaxy. So they're actually also liquid phase epitaxy. This is mainly for 3-5 for like common semiconductors. And they're also solid phase epitaxy. And there are many more like MB, MOCVD. There's many for 3-5 materials. For silicon, we mainly use VPE, vapor phase epitaxy, or thermal CVD. And this lecture is focused on some basic concept of thermal CVD or epitaxial by using Wafer phase. So Wafer phase epitaxy. Okay, so this is epitaxy, and we just stop here, and then I just want to show you, continue to show you their etching process from the CVD.